We now consider the JK flip-flop, and the first task that we want to find out is that how do we develop or design JK flip-flop from the SR flip-flop. And since we already made the SR flip-flop and we know its internal structure, without necessarily going back there, we symbolically use this symbol to represent SR flip-flop. Remember that it had gates G3 and G4 that had inputs S and R, and the other input for the two gates was the clock pulse, that you remember. And therefore, if we consider now that as the black box represented by this symbol, then we say that the input to Sn is now a combination of a J input and the Q bar of the SR flip-flop. And similarly for the AR, the input is a K and the feedback of Q from the SR flip-flop. That forms our JK flip-flop, and therefore we say that the input to S is going to be an add operation of J and Q bar, and the input to AR is an add between K input and the Q from SR flip-flop. So having said that, we will need to analyze how the new flip-flop JK would behave at different possible inputs of J and K combinations. So here we'll talk about an analysis table just to understand what will be the next state when we know J and we know K, and since we are forming the J flip-flop or JK flip-flop from SR flip-flop, then we can also consider what S is and R is at different positions. Since we have said that J is equals to, or rather S is equals to J Q bar and R is equals to K Q. So we will just list them down here as our inputs. So we have input J, we have input K, we have the present state Q, we can call it Qn, and we can also have Q bar, so Qn bar, and we can have now our S, which is the output of this, and R as the output of this. And then we ask ourselves what will be the next state, which is going to be measured by Qn plus 1. So for instance, when we say that let J be 0 and K be 0, and the previous state was 0, of course the Q bar will be 1. What will be S? We can simply see that S is J Q bar, which is J and Q bar. This becomes a 0. And what is R? K and Q, which is a 0. And therefore, since we know the next state is determined by the inputs of SR, we know that the next state will remain to be what it was, and it was 0. Therefore, the next state will be 0, which is we call Qn. And then we consider the other possibility that still our J is 0 and K is 0, but the previous or the present state was 1. Therefore, the Q bar will be 0. What we know is that S is this times this, which is 0, and R is this times this, which is 0. And therefore, the next state, though Q was, so the next state will be Qn. We know that SR says that when S is 0 and R is 0, the next state is going to be Qn. And this time, Qn was 1, and therefore this becomes 1. So we can do the analysis similarly for all of them. The only one that will be different is when we have J is 1 and K is 1, because what this will do is that they will be different from when S was 1 and R was 1. Remember, one of the states that we don't use in SR flip-flop is when S is 1 and R is 1. That is why the JK was developed, to mitigate that ambiguity, and that is going to be seen at this point. So for instance, when we have J is 0 and K is 0, and the present state is 0, of course the Q bar becomes 1. we ask ourselves what is S, and S is this times this becomes 1, and K is this times this becomes 0, and therefore when we have S at 1 and R at 0, we know the next state is going to be a 1, which is opposite of what we had here. We will see this is equal to Q bar, Qn bar, or the present state negated. Let's now observe the other one, 1, 1, and Q was 1, therefore Q bar is 0. We ask ourselves what is S? S is this times this, or is 1 and 0 becomes 0, 1 and 1 becomes 1, and therefore we ask ourselves when S is 0 and R is 1, the next state is going to be what? And we know from the characteristic table of SR that is a 0. So again, this is equals to Qn bar. So what you observe is that for the JK free-flop, our inputs J equals to 1 and K is equals to 1 are giving us opposite of what J is equals to 0 and K is equals to 0 are giving us. These are giving us the next state as Qn, whereas the J is equals to 1 and K is equals to 1 are giving us the next state as Qn bar. And for that reason, we can develop the characteristic table of the JK free-flop. But before that, we see the full developed analysis table of our JK free-flop, the one that we didn't finish. We just assume that this one you can also learn, do it yourself. It has been done here. The only thing that we have illustrated is this last section and the first section, and you can see that these two agree that the next state of JK free-flop when J is 0 and K is 0 is Qn, but when it's 1 and 1, then the next state becomes Qn bar, and that now allows us to develop our characteristic table of JK free-flop. And from what we have developed, we just need to say that when this is our input, J and K, the present state Qn, and the next state Qn plus 1. We have said we can always arrange this one the way we normally do, and we have seen that the next state, you don't have this one, this column for the characteristic table. The next state is going to be Qn 0, 1, but this is going to be Qn bar. That is the only difference that we have developed, and this becomes the characteristic table of our JK free-flop. So having developed the characteristic table of JK free-flop, we now move and discuss the excitation table. And the excitation table of a JK free-flop or any other free-flop is always generated from the characteristic table. And since we have seen our characteristic table as J, K, and the next state, this is how we have developed our characteristic table of JK to be. This is the only thing that came out differently for JK in comparison to SR. And therefore from this we ask ourselves, if we have the present state and we want the next state, what are the required inputs? That is what the excitation table asks. So we know our present state is Qn and our next state is Qn plus 1. Our required inputs are J and K, and therefore we ask ourselves from this table, if we are moving from 0 to 0, what do we require our JK to be? If we are moving from 0 to 1, what should be JK? Similarly, 1, 0 and 1, 1. So if we look at the first one, when we normally look at this one, if it was, remember that this could have been 0 or 1. So if it was 0, it remains at 0. If it was at 1, it remains at 1. So we're asking ourselves, if we want to move from 0 to 0, we can consider this one possibility and this other possibility. And for that reason, we say that we require J to be 0 and K, we don't care. We want to move now from 0 to 1. From 0 to 1, we can look at this one is giving us from, it might have been 0, it became 1, but this one can also have been 0 became 1 and 1 became 0. So this is one we can consider this as a possibility and the third one as a possibility, because it might have been 1 remained 1, or it might have been 0 came to 1. So we are going to consider these two, and therefore we say that j is 1 and our k is a don't care because it's changing. Let's look for the third one. We want to move from 1 to 0. So this is one possibility in which we can move from 1 to 0, and this is the other possibility in which we can move from 1 to 0. Because it might have been 1, it became 0, or it might have been 0 remained at 0. So this is another possibility. And since we have those two possibilities, we are going to say that j is a don't care because it can be 0 or 1, but k is a 1. So we say x is and 1, our k is a 1. And finally, we want to move from 1 to 1. And what can give us 1 to 1? This cannot give us 1 to 1, but this might have been 0 became 1, or it might have been 1, or it might have been 1 remained at 1 or 0 remained at 0. So we are going to consider these two possibilities. And for that reason, we are going to say that j is a don't care and k is a 0. So that becomes the excitation table of our JK flip-flop. And as you can see, this is what we have right here. That is the excitation table of the JK flip-flop. The last thing for the JK flip-flop we want to look at is the state diagram. And the state diagram normally comes from the excitation table. So since we know this is our excitation table that we have developed, we can clearly see that we have two possible states. The possible state might have been a 0, and the next state may be a 1. So we might transition from 0 to 0, we might transition from 0 to 1, 1 to 0, or 1 to 1. So we ask ourselves, what are the required inputs? This is just a diagrammatic representation of the excitation table. So we know for us to remain from 0 to 0, we require j to be 0. K is a don't care. For us to move from 0 to 1, we require j to be 1. And for us to move from 1 to 1 in this row, or rather in this row, we require k to be 0. And finally, for us to move from 1 to 0, which is this transition, we require k to be 1. So as you can see from this diagram, this is what we have developed right here. These are exactly the same, except that I have interchanged the 1 to be on this side and 0 to be on this side, but they are exactly the same.